Hello all, welcome back to Sri Sai Tech Edu YouTube channel, Read, Lead, Success. I've already started with the subject Network Analysis and Control Systems, already done with Module 1 topics. If you have not watched, please do watch Module 1 topics. In Module 2, we have started with the first topic, that is two-port networks. In that we have seen some concepts in the previous video. Today we'll learn some new concept. We've already seen one port network, admittance parameters. Now we will see some equivalent networks. We have already seen many of the sums till now from module 1 till module 2. There are some equivalent circuits which are one port, two port. So we will see some equivalent networks which we have already studied and which we have already done in module 1 in this topic. So some equivalent networks is nothing but some networks we are going to learn in this and some problems. First, before starting with the some equivalent networks, we need to know some formulas here. First thing is the voltage gain GV. It is mentioned by GV. GV is equals to V2 by V1. Then the current gain GI is defined as I2 by I1. The power gain GP is equals to power out by power in. That is nothing but real part of minus 1 by 2 V2 into I2 by 1 by 2 V1 into I1. The input impedance Zn as the ratio of input voltage to the current. We know that input impedance of the resistance is equal to V by I. So Z input impedance is nothing but V1 by I1. Output impedance is nothing but Thevenin impedance, that is ZTH, which we see at the output. It is minus V2 OC by I2 SC, nothing but V2 by I2. These formulas are required to solve one of the problem in future slides. So these formulas you need to remember. Why? Because they'll ask question to find voltage gain, current gain and the power gain and input impedance and output impedance. So you need to know these equations. Then here if you see there is a network. Here if each two port has a reference node that is common to its input and output port. If you see here, if this is the input, you know that. If these two input has a common node, so they are telling that only, that if each two port has a reference node that is common to its input, it is common. Again this is also common, and output port is also common. Input port and output port is also common. So it is nothing but it is connected in the form of parallel, we can say. And if the two ports are connected in parallel, so that they have a common reference node, then all ports remain ports after the connection. Thus for the network, for the network A, what we can write, how we can write is IA is equals to YA into VA. We know already that I is equals to YV, admittance into V. So I is equals to YA into VA we can write. Then IA is what? IA1, IA2. VA is what? VA1 and VA2. Then for the network B also we can write IB is equals to YB into VB. So VA will be equals to VB will be equals to V. This voltage VA will be equals to VEB is equals to V. And I, total current I is equals to IA plus IB. Okay. So totally how we can write the combined equation is I is equals to YA plus YB into V. Right. So, and we see that each Y parameter of the network is given as the sum of the corresponding parameters of the individual networks. Nothing but Y parameter, total Y parameters we get by parameters of A network, admittance parameters of B network. Addition of both we get the total Y parameter network. This is one of the equivalent network that it is mentioned in the textbook. This may be extended to any number of two ports connected in parallel. Like it can be network C again, network D. Like that it can be any number. So then what it happens, I is equals to YA plus YB plus YC plus so on. How many ever networks if they are in parallel into V we can write. So any number of networks can be connected in parallel. This is the procedure we are going to follow. Now we will see some sums that we have already studied in the previous modules. The same concepts have been repeated here. Why? Because we are learning port networks. So one port network, two port network. So they have repeated here some of the concepts. So we will see some sums. Find y and z out for the terminated two port shown. They are asking to find z out and as well as y parameters. That is what we have seen in the previous topic. That is admittance parameters they have already seen. Anyway, I'll solve here how to find y, but if you are not understanding, a clear video on y parameters, that is nothing but admittance parameters, is there in my previous video, that is part 2. You can go and watch once again. In that there are some problems. Now we will go with this sum. If you see here, we can here the mentioned is that I1, we want two port network. It is two port network we need to consider. Other than two port network, we can remove the other things. We can remove other part. So that 200 ohms and Vs can be removed and 1 ohm can also be removed. We just want a two port network, that is I1, I2, V1, V2, where it is mentioned. So I have written in that way. That is I1, I2, V2, V1 and other network. We need to apply KCL to this V1 node. When you apply, I1 is incoming current. So I1, summation of incoming currents. This is one incoming current and this is one incoming current. So we add them both, I1 plus 10 power minus 3 V2, that is equals to outgoing current V1 by 5K. We will write. Then after calculating, we get I1 is equals to 2 into 10 power minus 4 V1 minus 10 power minus 3 V2. If you observe cleanly that it is in the form of I1 is equals to Y11 V1 and Y12 V2. So Y11 is 2 and Y12 is minus 10 power 3. We got to know from this. Then now what we should do? We need to apply KCL to the next node. When we apply KCL to the next node, then if you see I2 is the incoming current and this is also incoming current. Summation of two incoming currents, that is I2 plus 20 I1 equals to V2 by 3K, that is outgoing current. So if you calculate this and substitute, and if you take left hand side on the right hand side in the form of I2 equation, I2 will be equals to minus 4 into 10 power minus 3 V1 plus 20.3 into 10 power minus 3 V2. So here if you see, if you compare, I2 is equals to Y21 V1 plus Y22 V2. These two are Y parameter equations, general equations. So from this we got to know the Y parameters, that is 2 into 10 power minus 4 minus 10 power minus 3, then minus 4 into 10 power minus 3, 20.3, 10 power minus 3. Now we got to know this. From here what we want Z out. How to find Z out? Z out is V2 by I2. We have already seen the previous formulas. Z out is nothing but V2 by I2 or V2 OC by I2 SC. For that what we need to do? I1 should be short circuited. So because we require V2 OC, V2 open circuit. So I1 1 equals to 2 into 10 power minus 4 into 0. V1 will be 0. V1 is 0. So you will get 1 is equals to minus 10 power minus 3 V2. From here V2 you will get a value. We will get some value V2. We will consider this as third equation. Then I2 will be equals to, if we take this I2, since V1 will be 0. Why? Because we want V2 open circuit. We want I2 short circuited. So for I2 short circuited, V1 will be equals to 0. So V1 will be equals to 0. You will get 20.3 into 10 power minus 3 V2. I2 SC is equals to 20.3 into 10 power minus 3 V2. After this, for this V2 OC will be, this V2 is nothing but V2 OC. V2 OC will becomes minus 1000 V after calculating. After then, if you substitute V2 OC in the I2 SC equation, then you will get I2 SC as minus 20.3. So Z out is nothing but V2 OC by I2 SC. You will get as 49.26 ohms as the Z out. Then use delta Y and Y delta transformation to determine Rn. As you know, we have already seen y delta, delta y transformations in the previous video. If you don't know, if you want some more other questions on y delta and delta y transformation, you can check my previous videos in the playlist module 1. So there is delta y and y delta transformation, that is general network transformation. You can check the videos, you can do some other problems which I have mentioned. Here same this kind of problem you have done in that topic. They have once again shown here, given in the sum equivalent networks for in this module, because it is one port network. If you see, there is only one port. This side there is no port, so it is a one port network. So they have took this as one of the kind of equivalent network. They are asking for Rn. As it is very easy. If you see, this is in the form of delta. Resistance here, like if this resistance is like this resistance is like this is the delta network. So delta to star we can convert. If you see here, see, it is in the delta, we can convert into star, that is R1, R2, R3. How you will get R1? Easy technique. I have already, there is in shorts also how to find the easy network, for the easy way to find the delta y and y delta in the shorts or the YouTube shorts, and there is video on also. But once again I'll tell, if you want R1, what we should do? We need to multiply the adjacent resistances, that is 47 into 47 by 47 plus 47 plus 47, that is all the resistances addition which is there in the delta. So you will get 15.67 ohms. As you can see, all the resistances are equal. So for all the R1, R2, R3, the value will be same, because for both things we want to multiply, then divide it by addition of all the resistances. So R1 equals to R2 equals to R3 is equals to 15.67 ohms is the answer. Then you will write in this form, this network. If you see 47 and then 15.67 is connected in this way, which I have shown in the previously, how we are converting from here to here. So you need to remove that other delta form to star form, you need to convert. After converting, these two are in series, these two are in series, and these two are in series. Series, what you will do? You will add. After adding up, if you can see, there is again another network where this is also in the form of delta, this is also in the form of delta. You can convert any of the delta into star, but I have took the upper one, convert into delta into star. If you want, you can try with the down network also into star, and you can get the answer correct. If you see here, again we need to find delta to star. If you get for R1, what we do? We multiply 62.67 into 62.67 by addition of 47 plus 62.67 plus 62.67, you will get R1. After that, for R2, what are the adjacent resistances? 47 and 62.67 by total resistances addition, you will get the R2. Then R3 also similar way, the adjacent resistances you are going to multiply and divide it by summation of all the resistances. Then after that, the network looks like this. If you see here, these two resistances are in series and these two resistances are in series. As they are in series, you add up. After adding, this 17.091 will be same, and as these two are in series, you will add up. So 64.091 and here 22.789 and 60. Here again this is in series, no? That if you add 85.459. If you see, these two are in parallel. If there is in parallel, you need to do in this way. If you consider 64.091 as R1 and this as R2, then if it is in parallel, how you will calculate? R1 by R2 by R1 plus R2. If you do this, you will get as 36.624 ohms. After getting that, if you see these two are in series, add up, then you will get 53.715 ohms. Then use delta y and y delta transformations to determine Rin for the network shown in figure. If you see, again we need to do delta y delta transformations. If you see here, you can convert any of this star or this star or this star into, sorry, not star, delta into star. You can convert, there are 4 delta forms. You can convert this or this or this or this into star. But I have took one of the delta as to convert into star. If you see here, this is R1 have 1, they R2, R3. We need to find R1, R2, R3. For R1, what are the opposite resistances? That is, that opposite nothing but adjacent resistances, that is 18 into 3 by addition of 18 plus 3 plus 6, that is 27. We will get R1. Then R2, for R2, what are the adjacent resistances? 3 and 6 are the adjacent resistances. So you need to multiply those two divided by all the resistances. That is nothing but the delta resistances, that is 3, 18 and 6. If you add, then you will get 27. So it is 0.67. To R3 also, the adjacent resistance are 18 and 6. You multiply them both and divided by 27. So you will get 4 ohms as the R3. After that, the network looks like this. If you see here, these two are in series and these two are in series. Then you can add up, you will get 2.67 and 2 ohms. And again, once again, if you see, we need to convert this delta into star. To converting delta into star, again use the same trick, that is R1, that is adjacent resistance 12 into 1 by 15 ohms, that is 2 plus 1 plus 12, that is 15 ohms. We divide it with the resistance of the delta, you will get 0.8. R2, our adjacent resistance are 2 into 12, we multiply it with that and divide it by our addition of the delta resistances, that is 2 plus 12 plus 1, that is 15. Then for R3, 2 and 1 are the adjacent resistances, multiply them and divided by 15. Then the network looks like this. If you see here, these two are in the series form. So you can write as 2.8. Again, once again, this is in the delta form. This is in the delta form. Again, you will convert into star. To convert to star, again follow the same R1. Opposite the adjacent resistance are 2.67 and 2.8, 7.07. I am not repeating once again. Do as per like this. Do like this only. Follow the same way. That is, you multiply the adjacent resistances divided by the delta form what you have considered, that resistances addition. That is 2.67 plus 2.8 plus 1.6. You get 7.07. After that, the network looks like this. When the network looks like this, if you see these two are in series and these two are in series, if you add, you can add up. After adding it, the network looks like this: 0.60, 0.77 and 9.60. And these two are in parallel. In the previous problem also I have told how to find the resistance in parallel. You will get as 0.709 if you calculate these two in parallel form. Then you will get the network like this. As these two are in series, you add up, you will get 1.311 ohms as the Rn. Determine the input impedance Zin of the one port shown in figure if omega is equals to 50 radians per second and 1000 radians per second. Now we will see how. This looks little bit different for the questions what we have done till now. Why? Because here inductors and capacitors are coming to the picture. So what we can do? It is easy. We will do that. If you see here, we need to convert. We can't directly convert this. You can see that this is in delta. You can't directly convert into star. And here also you can see this is in delta. You can't directly convert into star. There is some procedure for inductors and capacitors. Inductors and capacitors need to be converted into impedance. So how we can convert? How to convert is, these are the formulas. If you want to convert an inductor, that is this is an inductor, into impedance, then Z is equals to JXL. XL is the impedance, reactance of the inductance, reactance of the inductance. So JXL is equals to J omega L. XL is nothing but omega L. Then Z is equals to minus JXC for capacitor. Capacitive reactance XC is then minus J by XC will be equals to 1 by omega C. And XL will be equals to omega L. I hope you understood. We need to convert all the numbers into this form, all inductors and capacitors. How? See, now if you see, I'll tell for one inductor and one capacitor, you need to understand other things. For example, think that is L is 5 Henry they have given. Okay, for this 5 Henry they have given. How to convert into impedance? Z is equals to J into XL. So J into omega L. Omega, how much they have given for? I am doing initially for 50 radians per second. For A, 50 into L, 5. So 250 J is the answer. If you see here, 250 J. I have took as ohms. That is, we are converting into impedance. I hope you understood. Then inductor is done, one inductor, and one more I will show for capacitance so that you will understand. For capacitance I will consider 0.02 farad. If you see, Z is equals to minus j xc, that is equals to minus j into 1 by omega c. 1 minus j into omega, what we have considered here initially the first question, that is 50 into c, what is the value you have, 0.02. If you calculate this, you get as minus 1 j ohms. If you see here, I mentioned the same, minus 1 j ohms. Nothing but we are converting this capacitor into resistance. You can see I have even changed it into resistance. Nothing but minus 1 ohms. In the same way, we convert other inductors and capacitors into this form. How? If you see, 1 Henry is converted into 50 J. Then 2 Henry, if you apply these formulas, you will get 2 Henry. If you apply, you will get 100 J ohms. In the same way, minus 0.4 J ohms and 150 J ohms. We are converting into nothing but resistance. After converting, what we'll do? Similar again. If you see, this is in delta. From delta to star you need to convert. After converting, for delta star you know that 250 J ohms, 50 J ohms, 250 J ohms, minus J ohms. Here this is R1. How we got R1 here? R1 is equals to R1 opposite adjacent resistances are 100 J into 150 J divided by, what are the total resistances of the delta? 100 J plus 150 J plus, it is J plus but minus, it is 0.4 J. Okay, if you calculate this, you will get R1. In the same way, for R2, the adjacent resistances, two adjacent resistances of the R2 are what? 100 J and minus 0.4 J. If you multiply that and divide in the same way what I have shown for the previous one, and the previous question also clearly mentioned how to do. Here I am not mentioning because you need to know how to do from now. So, but you need to calculate and only write. But I am not mentioning here, but you need to calculate at R1, R2, R3. Then only you need to mention in the question, in the answer. You will get directly these values. After getting, if you see, these two are in series and these two are in series, add up. After adding up, you will get the network in this way. And see this, these two are in parallel. For parallel, what you will do? 249.76 J into 59.096 J by 249.76 J plus 59.096 J you will do. Plus again, if you see, if this is in parallel and in turn they are in series with 50 J and minus 0.160 J ohms. So only I have written in this way equation. If you see this in this way, so if you calculate the parallel equation, you get 47.789 J ohms. After that, if you can add up these all three. That is what this equation represent. If you add those all three, you will get 97.629 J ohms. Again, these two are in parallel. Parallel, if you know that 250 J into 97. Wait, here there is no place. So what I'll do is, if you consider this as R1 and this as R2, what you will do, if there are two, even this also same way, if this is R1 and this is R2, to parallel equation, how you will do? R1 R2 by R1 plus R2. I hope you are understanding it. You need to know basics. To know basics, module 1 first part you need to learn. Why? Because parallel, series, parallel, this comes in the whole subject of the network analysis. So you need to know, but in all modules, in all the topics I am explaining how to do as of my how much ever I can. But you need to know the things, simple things like series resistance, parallel resistance, you need to know. 70.2 J ohms is the final answer. Why? Because if you do this parallel equation form, if you put formula in parallel equation formula, then you will get 70.2 J ohms. Now we have seen for 50 radians. Now next we will see for 1000. Similar way. For 1000 ohms, what happens? If you see, this is JXL, no? J into XL, nothing but omega L. omega is 1000 into 5, nothing but JXL. For inductor, J into omega L, J into omega is 1000 into L is 5. So you will get 5000 J. First we will convert all the inductors. Then we will get easily understand. JXL, that is 5000 L. For again, if you see here 1H, that is 1000 J, and here 2H 2000 J, and 5H 5000 J, and 3H 3000 J. Nothing but we are multiplying it with the omega L. Omega into Ly, because they have given the omega value. Then for capacitor, what we will do? Minus J by omega C. If you calculate minus J by 1000 into 0.2, then you will get minus 0.05 J ohms. In the same way what we have done in the previously for 50 radians, we will do the same method here. After doing, you will get the equation. Again, this is in the form of delta. Convert into star. When converting into star, you will get the equation in this form. You just mention that this is R1, this is R2, and this is R3, and how to say, see, this is R1, this is R2, and this is R3. Same way, how we will do for delta and star, that is for R1, 2000 and 3000 J ohms are the product we need to take, divided by 2000 J plus 3000 J plus minus 0.02 J ohms. So you will get as 1200 J ohms. Okay, you need to have paper and pen when you are solving this. So only you will then only you will understand, but you otherwise you will not understand. Then later, in the same way, these two are in parallel, and if you calculate, you will get 967.741 J ohms. Again, if you see these all three are in series, then what you will do? You will add up. After adding, equation the network looks like this. Again, these two are in parallel. Calculate for the parallel equation. What the value will get is 1412 J ohms as the input impedance. Okay, it's easy. You need to understand the concept. If you are not understanding star delta, why? Because I have already in this topic only one star delta I have clearly done. So here I am not clearly mentioning how to do delta and star. If you want star delta clearly how to do, please do watch my YouTube shorts, or you can watch my star delta general network transformation in module 1 topic. You, after seeing that, you will understand how to do star delta transformation. Here also I explained in the previous sum. So you should, I think you will be knowing. So only I am directly writing, that is star to delta, delta to star. You got like this. I am directly writing. Okay, I am not mentioning how to do. Okay. Employ appropriate technique to find a value for the input resistance of the one port network presented by the schematic. If you see, after seeing this, you feel like, oh my god, how much stuff it is. No, it is very easy. Again, here also you need to appropriate nothing but star delta only we need to find. Here many delta star conversions will be done. If you see, that is in the whatever I am highlighting there, that is in the delta form. You will convert into star. After converting this to star, you will get 1, 0.67 and 2. Again, if you see, after getting that, these two are in series and these two are in series. So 12 plus 2, 14, and this is 5 ohms. Again, 5 ohms and 14 ohms are in parallel. If you calculate that, you will get 3.684 ohms. Again, if you see here, these two are in series. If you add up, you will get 4.354 ohms. And other network is same. Again, if you see here, that here this is in the form of, again in this form only, see, again in this form it has come here. So again it is in the form of delta. So delta to star we need to convert. After converting it again to star, you will get the equation in this form. Again, if you see these two are in series, you can add up. After adding up, the network looks like this. Then after finding this, you will get, if you see again, these two are in series, 9.705. Again 3 ohms, 10 ohms, everything is same. And if you see this, that again, if you see, this is in the delta form. If you convert that into star form, then what happens? You will get a resistance in this. This is the star form what you get for this delta. So after finding that, you will get the values like this. That is 5.514 ohms and 5.136 and 2.531. That is nothing but you are adding up these two. Why? Because they are in series connection. After that, if you see 3 ohms, 10, these two are in series and these two are in series. If you add up, the network looks in this way, and the 3 ohms and 1.178 ohms and 12.566 and 6.064, these two are in parallel. These two are in parallel, in turn they are in series with the 3 plus 1.178. You find first this parallel, then add with 3 and 1.178, you will get as 8.268, 8.27 ohms is the answer. See, I can't do for delta star for all the equations. I can't show you. So you should know how to do star delta transformation in a quick go. So only I have made the YouTube shorts so that it for the easy trick to remember star delta conversions. So I can't show everything. Here many times I did delta to star conversion. You should know how to do that so that these equations to solve and finding the final input impedance will be easy. And now we will see that let for the two-port network. This is the two-port network. Y is equals to, they have given the Y parameters already, 0.1 minus 0.05 and minus 0.5 and 0.2. That is Y11, Y12, Y21 and Y22. They have already given. They want what? That is GV, GV voltage gain, current gain, power gain, input impedance and output impedance they want. What we have seen initially, some formulas you need to remember, I told you, the first slide. Based on that, this problem is it. Now first we can write, using this you can write the equation, that is I1 is equals to Y11. Y11 is 0.1 V1, Y12 is minus 0.05 V2 and I2 is Y21 V1 plus Y22 V2. Nothing but Y21 is minus 0.5, Y22 is 0.2. As you know, these are the admittance parameters. So you can directly write the equations in I1 and V1 and V2 terms, I2, V1 and V2 terms in this way. From this, we can, after that, from the figure, we need to apply the KVL to mesh 1. KVL to this mesh 1. This is if you consider as mesh 1 and this as current, this as mesh 1 and this as current I1. What you will get that, see, V1 plus V1 plus minus 10 I1 and minus V1. Okay, so V1 minus 1. Vs is nothing but 1. So V1 minus 1, that is equals to minus 10 I1. You are going to write the first equation. The second equation is, there is only one equation. This is V2 equals to minus 5V2. 5 I2. If you consider in this way, if you consider I2 as the current flowing through this, V2 is equals to minus 5, I2 is the second equation. It is simple. KVL to apply. Then now substitute these 2 equations in A and B. We got to know V1 and V2. So substitute in these two so that the equation now will be in I1, I2 terms. That is 2I1 minus 0.25 I2 is equal to 0.1 after substituting V1 and V2. And again, if you see for I2, for this equation, minus 5I1 plus 2I2 is equal to minus 0.5. If you solve that third and fourth equation, you will get I1 and I2 values. After get I1 and I2 values, what we need to do? We need to substitute in V1 and V2. That is, now put I1 and I2 values in 1 and 2. So you get V1 and V2. V1 will be what? 0.073. V2 is 0.91 volts. After getting this, it's easy now. We got to know V1, V2, I1, I2. So you can directly find GV, GVI. See, GV formula we have already seen in the first slide. That is, GV is equals to V2 by V1. That is, you divide V2 by V1, you will get 1.246. GI is what? I2 by I1. I2 by I1. I2 value is what? You got minus 0.182 and I1 is 0.27. If you divide it, minus 6.741 is the GI, that is current gain. After that, GP, power gain. GP formula is minus V2 I2, that is power of the output side, that is V2 and I2 by V1 by I1. V1 I1 divided by V1 I1. So if you put those values and find, GP will be equals to 8.402. 8.402. Then if you want Z in input impedance, V1 by I1, you know V1, that is 0.73, I1 as 0.027, you will get as 27.03 ohms as the input impedance. Z out is what? V2 by I2, minus V2 by I2, minus 0.91 by minus 0.182, you will get 5 ohms as the Z out. So simple it is. You need to apply KVL initially. After applying KVL, you substitute that V1 and V2 in I1 and I2, you will get I1, I2 values, and nothing but we want I1, I2 and V1, V2 values. For finding that I1, I2 and V2 values, after finding I1, I2, V1, V2 values, you substitute in the formulas, you will get all the values, GV, GI, GP, Zin and Z out. So easy. These are some practice questions which I've already solved. This kind of questions, if you see this kind of question, I've already solved similar question in previously, that we need to convert the inductor into resistance impedance and capacitor into impedance, and find put star delta star conversions, and you'll get the value. Omega is equals 15,000. The answers also are given. You can recheck with this answers. Then this also using star delta transformations you can do, and you'll get the values. So I'm stopping the video here in this by this topic. We have already done with one port network, admittance parameters, and some equivalent networks in the chapter 1 of module 2. So we are left with 3 more topics, that is impedance parameters, transmission parameters, and hybrid parameters in the chapter 1 of the module 2. So in impedance, I'll do the impedance parameters, transmission parameters, and hybrid parameters separate video in the next video. That is separate the one concept, separate videos only I am planning, so that it will be easy for you also, and all the sums will be covered. So for now I am stopping this video till some equivalent networks. Thank you from Sri Sai Tech Edu YouTube channel. Read, lead, success. Keep reading.